Assalamualaikum warahmatullahi wabarakatuh. My name is Najib Rashdan from Group 10. So, shaft. Shaft is a member or a part a rotating part that used to transmit energy or power to another part. Usually, the shaft is supported by bearings and is connected to a set of gears or pulleys that used to connect to other part. So usually the force that acting on the shaft is bending moment, axial force and torsion. So for our project, we designed an important part of an engine that is a crankshaft. Crankshaft design is very important because the performance of the engine is depends on it. Our objective is to design a 4-cylinder engine crankshaft that has a maximum power of 100 horsepower at 4000 rpm. And secondly, our objective is to create a stress analysis for the crankshaft.
Assalamualaikum, my name is Muhammad Salih Aibi. Matrix number A162027. Okay, I'm going to talk about methodology. There are two types of crankshaft which can be differentiated by position of the crank. Those two are center crank and overhung crank. Okay, we choose center crank because the engine is 4-cylinder. Design procedure, I'm going to talk about it. The first three steps are the parameter of selected engine, load acting on the crankshaft, distance between support, and the respective position relative to the load are to be determined. Then main dimension of crankshaft is determined based on the factor of safety and yield strength. And lastly, the dimension are checked for maximum bending moment and maximum torsion. Okay, for factor of safety, the design is based upon the yield strength because failure on the crankshaft usually caused by bending and torsional stresses. Therefore, high factor of safety is used for our crankshaft. Okay, lastly for the crankshaft material. Because the crankshaft are constantly under high stress and fatigue load, thus a tough and fatigue resistant material are needed, which is in our case we use cast steel. Okay, why we use? Because cast steel have high strength and toughness. That's all from me. Thank you.
Hi, I'm Melin. I'm here to present the design and calculation for our crankshaft. 3. This is the sketching of our design. Of all, using a safety factor of 3, we can find out the allowable stresses. For the mean effective pressure, we use this formula to determine it. For maximum bending moment, horizontal reaction force at point 1 can be determined, and point 2 can be determined from this formula. For the petrol engines, the angle can be determined, which is 30 and 14.5 degree. We can use this angle to find the FQ, FT, and also FR. Thus, we will carry on to find out the tangential force and also radiation force by this formula. For the design of clamping, we have two cases. We will determine the clamping diameter from both cases, and we will choose the larger value. Choose 84 for the clamping diameter, and the length of clamping can be determined from this formula. The maximum bearing pressure of the clamping is around 9.8 to 12.6 for our case. Then we take it as 10 so that we can find the length of the clamping, and the length of clamping is 36.
Hi, my name is Muhammad Firdaus bin Yaakob, matric number A161326. And I'll be continuing with the calculation part. Firstly, I will talk about the crank rod. The crank rod is the arm of a crank which connects the crankshaft with the crank pins or two adjacent crank pins. Now, by using the maximum bending moment on the crank web here and the section modulus here, we can find the stress at the crank web due to the bending moment, which is 51.3 megapascal. The answer is less than the allowable stress, so we can conclude that the dimensions are acceptable. Next, by using the reaction force at point 2, we can find two things, which is the bending moment at shaft and also the twisting moment at shaft. By using this to answer, we can find the equivalent twisting moment at shaft, which is 5.54 meganewton mm. Now, by using this answer, we can find the shaft diameter, which is 88 millimeter. Last but not least, we will say about the design of the crank web. So, by using the direct compressive stress, we can find the maximum compressive stress, and also by using the twisting moment of the arm, we can find the shear stress of the arm. So by using these two answers that we found, we can find the maximum combined stress, which is 75.68 megapascal. This answer is less than the allowable stress, which is 83.33 megapascal. Therefore, the dimensions are acceptable. That's all from me. Thank you.
Hi, my name is Muhammad Aiman bin Hasran and my metric number is A160664. I will explain about the finite element analysis. The finite element analysis is the simulation of any given physical phenomenon using the numerical technique called finite element method. Engineers use it to reduce the number of physical prototype and experiment and optimize components in their design phase to develop better product faster. As we can see here, the crankshaft is constrained preparing in this area, and we use 3.33 kilonewton of loads of force toward the crankshaft, and we can get the first principal stress, which is this area is the minimum, which is negative 140.1 megapascal, and we can and the maximum is in this area, which is 757.9 megapascal. Next, we can get the third principal stress, which is this is the lowest principal stress, which is negative 389.9 megapascal, and this area is the highest, which is 261.6 megapascal. Next, the von Mises stress is 651.3 megapascal. Next, the highest displacement is in this red area, which is 0.1676 millimeter, and the lowest displacement is in this area, in this blue area, which is 0 millimeter. And the safety factor of the crankshaft is the minimum in this area, which is 0.38, and the maximum of the safety factor of the crankshaft is in this blue area, which is 15. For the conclusion, we can get the crank pin diameter, which is 84 millimeter, and the length of crank pin, which is 36 millimeter, and the web thickness, which is 52 millimeter, and the shaft length, which is 60 millimeter, and lastly we can get the shaft diameter, which is 88 millimeter. And that's all from me. Thank you.